Good, thank you. So, let's organize the notes slightly. Yes. So, I would like to start with saying just one word. This is some kind of another example of a Borel subgroup. So, we looked yesterday at Bn. So this is the standard Borel subgroup inside here An. Okay? And in fact, we can relativize this setting. And so I say I take Bny, which is just Bn with coefficients in the function field of y, where y is just any variety. And so this lives inside y times an over y. Okay? And this one here is then again a Borel subgroup of length 2n. Okay, and I didn't said anything about dimension 1. So here is also an example. So up to conjugation in here y times a1 over y, there are the Borel subgroups just b1 y and this non-split torus that we looked at yesterday. Okay, so where f is in ky not a square. Sorry, square free. Okay, good. And yesterday I wrote down a theorem that I would like to prove more or less. So let me recall it. So the theorem was, okay, we take just any g inside beer x. Maybe remember that x is always an irreducible variety over k, and n is its dimension. Yes, and our ground field k is just algebraically closed, characteristic is 0, and is uncountable. Uncountable. Okay, so the theorem is as follows. G is solvable, connected. Then we have first statement, let's call it A. So the length of G is smaller or equal than twice the dimension. And if the length of G is twice the dimension, then y is rational. So I have a birational map from y to an, which conjugates G to a subgroup of the standard Borel subgroup. So I have phi inverse composed with G, composed with phi is in Bn. Okay, so and as a corollary, I don't write it down once more, but as a corollary we get that any connected solvable subgroup is contained in a Borel subgroup. For that we don't really need this bound. This would also be, of course, with any bound, this would be possible. And what we also get is that Borel subgroups of length 2n are all conjugated inside the Cremona group. Okay, so I would like to give kind of a sketch. So let me start with point. I will start with first with let's say with the trivial case n equal to 1, because then one can do both. So in this case, the birational transformations, connected component of it, has just 3 possibilities. We had mentioned it a lot of times already. Oop. So, so either it is PGL, PGL2, or it's an elliptic curve, or it's just trivial, because I take here the connected component, and so we are fine, okay? I mean, only in this case I can have Borel subgroups of, or just solvable groups of length 2. Good, so we can assume that n is bigger than 1. Yes, and I will make a notation. So A should be the closure of the last non-trivial derived subgroup of G. Okay, so in particular, of course, this A is abelian, or maybe I prefer to say it's commutative. Okay, good. And now we distinguish 2 cases. Either this A acts with a dense orbit or it doesn't. Okay, so let's start with the case where it acts with an open orbit. So okay, x of A is the same as k. Okay, yesterday I wrote down a statement which says that in this setting, when A is commutative, A has to be an algebraic subgroup, and its centralizer is just A itself, and the dimension of A is equal to the dimension of the variety, so this is n. Okay, good. Now, this A is normalized by G, okay? I mean, it is just like the closure of the last derived the last derived subgroup is normalized by G, so it's closure as well. So we get a homomorphism from G to the algebraic group automorphisms of A, where I send G just to its conjugate. So A is mapped to G, A, G inverse. And let's call this iota. And the kernel is, of course, with kernel A. Okay, because it is self-centralizing, and so the kernel has to be A. And yesterday, we already found that this homomorphism really lands in the algebraic group automorphisms of A. Okay, this follows from the universal property of algebraic groups. Okay, good. Yes, so let's analyze this group a little bit further, because this will be used then in order to bound the length of G. Okay, so A is an algebraic group. So inside I have 2 prominent subgroups, A uff and A unt. I don't know whether they were already on the blackboard, maybe in, no. Okay, so this is the affine part, okay? So this means this is the, one can say this is the largest affine subgroup, largest connected. And this one here is the, I can say, smallest subgroup such that the quotient, smallest normal subgroup such that the quotient is affine. Okay, so these are two, and in fact A is generated by both of them. Okay, this is just general fact from the theory of algebraic groups. Okay, so when I have any automorphism of A, it then induces some automorphism on the affine part and also on the anti-affine part. Okay. Now this guy here is countable. And inside here, maybe I should analyze AF slightly further. So this is a commutative algebraic group, and we are in characteristic 0. So it is really of the form gm to some power p times ga to some power q. And the automorphisms of that guy here, again, give only countably many. So, and the automorphisms of that guy here is just, maybe I write here gm. The automorphisms of that guy here is just the linear maps of GA. So what I find here is a GLM of countable index. Okay, good. And now I can take the pre-image of this guy. So this is over K. And so this is inside G of countable index. Okay? Hence, from yesterday, the length of these two guys, also length of the inverse of GLMK, is the same as the length of G. Okay? And with this, we can now make the bound. So then the length of G is bounded by the length of the kernel. I mean, the length of G is now the same as the length of that stuff. And kernel here is A, so it is just 1, the length. And then the length of the image is the length, the biggest length that I can get for a solvable, connected solvable group inside GLMK. Okay, so here I just get M. Yes, and this is of course bounded by 1 plus n, which is strictly less than 2n. Okay, so with this we proved the first statement, but we also proved the second statement. It just doesn't appear. Okay. Good. And what I also would like to mention, this M here is in fact exactly the dimension. Sorry, I should write it this. Dimension of the unipotent elements in A. Okay, good. So that was about the case when A acts with a dense open orbit. So let's go further to the case when it doesn't act with an open orbit. Okay, so what we can do here. Yesterday I introduced the Rosenlicht quotient. So let's do the Rosenlicht quotient with respect to A. So pi from x to y is the Rosenlicht quotient for A. Okay, Secretly, I shrinked the x a little bit, but this is of course possible. I mean, I say stuff about birational transformation, so I am allowed to do that. Good. And what we see is that the dimension of y is, of course, strictly less than the dimension of x, because A is a non-trivial group. And by this assumption, we know that this is now strictly bigger than 0. Okay, so the dimension is really in between. And this is quite good, because the idea is to do somehow induction. Yeah? Yes. So for that, let me write down. I consider phi from G to here y, where I just send G into its induced birational transformation. This is possible as G normalizes A. It permutes the fibers of the Rosenlich quotient by A. Okay, so I get really here. Also this G is really inside what I called yesterday beer x pi. Okay, good. And this one here is continuous. So by induction, we have that the length of this image is really bounded by twice the dimension of y. Okay? And on the other hand, I look at the kernel of this map. So H is the kernel of phi. Okay. So here I have slightly a little problem, because now I would like to bound the length of H. Okay. But H is not connected. Okay. So when I pull it back to the geometric generic fiber, it's probably they're not connected. Okay. So I have really to pull back yes, I have to pull back the connected component. So let me say epsilon, this is just this pullback homomorphism to the geometric generic fiber. Okay. And then again here I can say that the length of epsilon h circ, which is the same as the length of h circ, is really bounded by twice the dimension of the geometric generic fiber, which is n minus the dimension of y. Okay, good. So now we would like to put everything together, but here is with the slight problem, but in fact it's okay. This guy here is G mod h, and not G mod h circ. But from yesterday, we have seen that G mod h is in fact the same as the length of G mod h circ. Okay, so putting this together, we are happy. Okay, good. So this was about part A. So let me give also a proof of part B. So still, as I said, in this case, we are done. So we still assume that we are in this case here. But now we assume also that the length of G is really 2n. And we want to show that in this case, y has to be rational. And yes. Okay, since this length is 2n, the length of these two guys, where I did somehow the inequality, have to be now equalities. So the length of h circ is twice, let's say, d, and d is n minus the dimension of y. And the length of phi g is twice the dimension of y. Good. So we do again the same. Also we still have here this Rosenlicht quotient, okay? And so I can study the pullback of A under epsilon. So this is epsilon of A bar inside the birational transformations of the geometric generic fiber. And the cool thing now is that if I look at the invariant functions here, so these invariant functions, xk is an integral scheme, and it's really just a reduced variety, everything nice. So this one here is exactly k tensor with kx over ky. Okay, so if I look at the invariance under A prime, I get here the invariance under A, but this one is k of y. So these are just constants, okay? So again, this A prime is something commutative, and we get that A prime is an algebraic subgroup. It is self-centralizing, and its dimension is equal to d. D is the dimension of the geometric generic fiber. Okay, so a bit as before, we considered a group homomorphism from, now I should introduce H prime. So this is the pullback of H circ, and taking the closure. So this one here normalizes my A prime, and so I get the group homomorphism like before into the algebraic group automorphisms of A, okay? Just by sending some H or H prime to, sorry, here's A prime, so A prime is sent to A prime H, sorry, of course the opposite, so H, A prime, H inverse, or here with primes. Okay, and the kernel is just A prime. Good. So as before, we can make oh, maybe I should use the other blackboard. So, as before, I can now make this this kind of bound. So, the length of H prime is bounded by 1 plus the dimension of the unipotent elements in A prime. Okay? And this one is bounded by 1 plus d. And on the other hand, we know that this one here is twice d. Okay? So this gives a constraint on d. So d has to be 1. And moreover, we see that the dimension of the unipotent elements of A prime is the same as d, okay, which is 1, okay. So this also gives us that the A prime is equal to GA over the algebraic closure of KY. Good. So yesterday we had this kind of descent of unipotent elements. And so A contains some unipotent subgroup. So this is isomorphic to GA. Okay. And this is somehow the important thing, that we have now some GA, sorry, not in A prime, but in A. Okay? So, let me write down some diagram. So here is my Rosenlicht quotient. So I can also make now a quotient by this U. So let me write it down like this, 2y0. Here it is birational, and so this is the quotient by U. Okay, and this is in fact birational to y0 times a1. And this is just given by the projection. Good. So very good. Down on y, we know that the length of phi g is twice the dimension of y. So by induction, we know already that y is rational. And yes, and that this image is inside the standard Borel subgroup of pure y. Okay. So the last thing that we have to say is the G is something solvable, and the kernel, this ETH Zürich, has length 2D. Okay. And with both of these, one can conclude that this G is in fact contained inside here y, semi-direct product with B1 over y. Okay? So this means now if I plug in this one here, okay, I really see that my G is in fact inside the standard Borel subgroup. And so this finishes the proof. Oop. So, okay, good. So I wanted also to say some stuff about Borel subgroups of a length 2n minus 1. So Borel subgroups of length 2n minus 1. So for that, let me recall from yesterday. So the Borel subgroups in here A2 up to conjugation are this non-split torus, and then there was like a semi-direct product of GM with Tx1 over A1 and the standard Borel subgroup. That one has length 4, that one has length 2, and this one has length 1. Okay? So what we see is that length 3 doesn't appear. Okay? So one can ask whether this is some accident or is this maybe some general phenomenon. Yes. And in fact, it is not an accident. And I also should say, very important, so this is joined with, this is some kind of a different project. So this is with Christian Urech and Susanna Zimmermann. And it is work in progress. Okay. Good. So, yes. So, as I already said, this is not possible, and I will come to it. But it is still possible that one can have Borel subgroups of length 2n minus 1. So let me give an example for that. So let A be an abelian variety. Or maybe I make it more like this. Let's say E is an elliptic curve. Curve. Good. So I can look at elliptic curve and semi-direct product with Bn minus 1 of E, okay, and I call this Cn minus 1 of E. So this is something which is contained inside the birational transformations of E times A n minus 1. And in fact, this one is a Borel subgroup of length 2n minus 1. Okay. Good. So, and in fact, our main result is that, yes, maybe let's write it down and then comment. So let's say G is in here X, some Borel subgroup of length 2n minus 1. Then we have two possibilities. Possibility A is X, so there is a birational map from X to An, such that when I conjugate it, my G, then I'm inside the standard Borel subgroup. And the second possibility is there exists a psi from X to E times An minus 1. Okay, birational transformation such that psi G psi inverse is contained inside Cn minus 1 of E. Okay, and then there are no other possibilities. Okay, so I would like also to give you some sketch of the arguments. So, sketch. So, as before, so A, this is in G, just as before. So meaning it is the closure of the last non-trivial derived subgroup. As before, I denote by x to y a Rosenlicht quotient for A. And I denote by H the kernel of my map from G to here Y. Okay, good. So with similar bounds as before, we have here two possibilities because the length is still quite high, so it is 2n minus 1. So either this d is equal to 1, let's say what d is, so this is n minus the dimension of y, exactly as before, or d is equal to 2 and all elements of A are unipotent. Okay, this is exactly, here we had it before also, so it's not, I mean, it contains some unipotent element, and for the proof this was here important, but in fact A consists only of unipotent elements, okay, because the pullback is an A prime, is a GA. Okay, so in this case here, it is, because there are a lot of unipotent elements, it's quite similar as before. So let's just say, okay, similar. One has to be a bit more careful, but let's say, okay, this is similar as before. And so we will concentrate on this case when d is equal to 1, okay? So we assume d is equal to 1. Good. So I want to introduce some, maybe write down here some diagram. So I have here my x, which goes to y, which is the Rosenlicht quotient. So I can shrink y a bit. I can enlarge x as well. So I can assume that this one here, maybe I do it this way. So this is still like the Rosenlicht quotient, and I can assume that it is smooth. And I can embed this in some closure such that, and I resolve everything and so on, so that this one here is a projective morphism which is smooth. And all fibers are one-dimensional. Okay? Good. So again, I look at the pullback homomorphism from beer xy to beer kxk, where again k is just an algebraic closure of y. Good. So in this case here, these are, of course, this is something one-dimensional and smooth. So these are really just the automorphisms of xk over k. Okay? So my epsilon a bar, which I will denote again by a prime, this is either rational. So this is, let's say, case A, or it is an elliptic curve. And we distinguish these two cases. Okay. And let's say I will denote by G prime, just for simplicity, the image of G in beer Y. Okay, so let's say we are in case A, so that this one is really a rational, is a rational algebraic group. Okay, so here we have again two cases, namely either the length of this image is either 2n minus 2, okay, or it will be 2n minus 3, but there are no more possibilities because of the whole group has length 2n minus 1, okay. Good. So in this case, again, the y is rational, and we have that this G prime, we can say up to conjugation, is really inside the standard Borel subgroup. Okay, good. So, but there is still a bit a question. We have this map here, but we would like to split off one A1, okay? If in order, I mean, you see, in the end we would like to show that that the x is either rational or it is of this form here, okay? So we would like to split off one A1 or P1 factor of x. Okay, good. And for that, we look at x bar minus x, okay? And this is exactly the fixed locus of my A. Okay, this here is a Rosenlicht quotient, and I have some kind of action here, okay? And these are exactly the points that are fixed by A, okay? Good, but we have now that down on the base, we have this G prime, which acts somehow not really transitively, but like it has a quite huge length, okay? And this enables us to give that this map here, okay, let's call it pi bar. Pi bar has a section. Okay, and then when this pi bar has a section, then we can further conclude that one can really split off one A1, or let's say it this way, this one here is then birational to y times P1. Okay, and again, the G is then contained in here y, semi-direct product with the P1y. So it's not possible that this A is somehow, sorry, I mean yes, that this A here is this non-split torus, because we have here really a section, okay? So that was the important step. Okay, so let me come to the second case when the length is 2n minus 3, okay? We have only these two cases. Okay. So by induction, this one here has now length 2n minus 3. So this is, yeah, which is the same as 2 times dimension of y minus 1. Okay. So by induction, we are either in that or in that case. Yes. Let me say the more interesting case is when this G prime is then really inside this Cn minus 2 of E, and my Y is birational to E times A n minus 2. Okay, so by this one is the dimension of Y is n minus 1, and so then by induction I'm in this case. Okay, good. And what one uses is that because the length is 2n minus 3, the length of H circ has to be equal to 2. Okay, and then as we did before, when the length is 2, I have something unipotent inside, and I have this kind of, that the G is really inside here Y, semi-direct product with E1 of Y. Okay, and then we conclude. Okay, that was about the case when this A prime is rational. And so let's come to the case where it is an elliptic curve. Yes. Oh. Yes. So I have here my Rosenlicht quotient again. And so yes. And in fact, in this case here, I mean, when this is here an elliptic curve, this means that here all the general fiber is a genus 1 curve. Okay, and so I have an action of an elliptic, also just to say over the generic fiber here, let's say over spec ky, x ky, I have here an action of an elliptic curve which is defined over this here, and it is homogeneous under it. Okay, so maybe let's call this elliptic curve E. And the good thing is, okay, this E of ky, this is, because we are over an uncountable field, this is not finitely generated. Okay? And then by a theorem of Lang-Néron, it has to be a constant elliptic curve. So this E is really of the form E0 times, let's say, ky. Okay? And E0 is now an elliptic curve over k. No, we don't. We a priori we don't have a section. Yes, yes. I don't say that this one here is an elliptic curve. I just say it is a homogeneous space under this elliptic curve. But it could be that this is a homogeneous space without points. Why E has one? I mean, you can think of. I mean, you can take, let's say, of this one here, you can take the pick 0, also the relative Picard variety, okay? And so this gives you then, and this you can see as the relative Picard variety, but of degree 1 divisors. And then I have an action of the pick 0 on pick 1. And this corresponds exactly to this. Okay, I didn't want to go into that because I thought it's like a bit more technical, and so I just wanted to say, okay, we are really in this situation. Okay, let me erase some stuff. Yep. Yep. Good. So this means that this stuff here is when we shrink y a bit, this is then a principal E0 bundle. Okay? So this one here, this is a principal E0 bundle. Good. So let me draw a bit more pictures. So I have, when I look at my G, where I have it, my G prime, this is, yeah, it's again, where I have it, it's over there, okay? So the G prime has, I mean, this one here, we know it is rational, so it is really like I can say I replace it with a n minus 1. and the G prime is really something which is inside Bn minus 1. Okay, so we are in that case. So when I take here now the derived subgroup of length 2n minus 3 of G prime, this acts just in the last coordinate by translations. Okay, so the picture is a bit like this. So these are somehow the fibers. So this is like an minus 2 times a1, and then I can project down to n minus 2, which is somehow the Rosenlicht quotient of this guy here. Okay, and above I have here my x. Good. And what I do now is I take back, I look at the situation in the geometric generic fiber of this guy here. So let's call this maybe rho. So geometric generic fiber of rho, okay? And for this, let's say L is an algebraic closure of this guy, of the function field of this guy here. So the situation I consider now is here XL over, this is then A1L, and this is over spec L. Okay. So, and now I can write down again this sequence. I can look at the birational transformations of XL, which preserve this vibration. Let's call this, in principle, it is like pi L, which goes down to the birational transformations of A1L. And in the kernel are the birational transformations of XL over A1L. So this is the kernel. Okay? Remember here now the yes, I mean the E is really E0 times KY. So what I have inside here is E times E0 times L. Okay, the pullback of the E0 which acts here. And in fact, this is exactly the connected component of this guy here. Good. Then inside here, I consider the 2n minus third derived subgroup of G, and I pull it back and take the closure. Okay. And this one here, when I map it down to here, it acts by translations. So it goes down here to GAL. Okay. So, and this one here is, in principle, maybe I have to do something a little bit smaller that I don't know, but it is like the most part is inside here, okay? So now this goes down to an algebraic group. The fiber is something finite dimensional, so this also has to be an algebraic group. And in fact, an algebraic group of dimension 2, okay? And it's an extension of GA by, maybe it is by something finite, then it's anyway one-dimensional, and so it's commutative. Or it's an extension by this guy here, but then it is still commutative by the decomposition into affine and anti-affine part. This would be exactly when these factors would be exchanged, then it can happen that this one here is non-commutative, okay? But here, it's exactly the GA is here on the target. So what we get, this guy here is commutative. So this says that this guy here is commutative. Okay? But the length of G is 2n minus 1. So that cannot be commutative, so we arrive at the contradiction. So this case that this last guy is an elliptic curve is not possible. I have still 5 minutes. Very good. Good. That was about proofs. Now I don't prove anything more. So I just state some things that I would like to mention. One question is about explicit exotic Borel subgroups in higher dimensions. Okay? In dimension 2, we have explicit exotic Borel subgroups, but in higher dimensions, it's not that clear. Okay? And in fact, yes, there is an explicit one. So, and the idea is quite simple, where I have it. There we have a Borel subgroup of length 2 in dimension 2. And what we do is just we take it. So Gm over, this is then an minus 2, semi-direct product with this non-split torus. So this is now not x1, so this will be x n minus 1 of n minus 1. Okay? So this is something that fixes the first n minus 2 coordinates. And so I can do the semi-direct product with standard Borel in this first n minus 2 coordinates. And this one is, in fact, a Borel subgroup of length 2n minus 2. So this gives an example of an exotic Borel subgroup for all dimensions. Good. Maybe what I also would like to mention, as Julia told me I should mention it, the technique that I introduced yesterday, together with somehow more stuff, also enabled us to something more, which is now not about Borel subgroups. So we also proved that, in fact, the group of birational transformations completely characterize rationality. So this one, when this is an abstract group isomorphism, maybe abstract is a bit strange, but it's just a group isomorphism, okay? I just mean it doesn't preserve anything. It's just a group isomorphism to beer an. Then, in fact, X is birational to an. Okay. So this one, and we proved it really just over, let's say, complex numbers, yeah, or just like the assumptions that I made, algebraically closed, characteristic 0, and uncountable. And it was already proven by Serge Gantin in case when the dimension of X is bounded by n, but one can do it without. So, yes. Yes, this was what I wanted to say. Also that it stabilizes some. I would more say it stabilizes a coflag. I mean, it stabilizes like when I project to Pn minus. So this one is stabilized. Yeah, also maybe it's not morphisms, they are rational maps, yeah. Yeah. Abstractly characterize this here. Yes, I would say so, because you say you start with your standard, as it's not a standard conjugate of a standard Borel subgroup, and then you derive twice, and you make the Rosenlicht quotient by this guy. Sorry, no, first you make the Rosenlicht quotient by the by that one of length 2n minus 2. And then then the next one would be by this one by 2n minus 4, and so on. So successive Rosenlicht quotients of derived subgroups. So this would be something intrinsic. Yeah. Or I don't know whether this was the idea. Okay. Okay, good.